On this slide, we have a handy summary table which has a lot of the information that we need to know about our subatomic particles. So probably the most important thing to know about the subatomic particles is their location within the atom. So we've talked about how two of these groups of subatomic particles are located within the nucleus. So that's the positively charged proton and the neutral neutrons. And around the outside of the nucleus, we have the electrons orbiting around that central nucleus. So the other really important thing to know is the charge of each of the subatomic particles. So the importance of this will come in, become a bit more clearer later in the session, but essentially we need to know that the protons are the positively charged ones, electrons are negative, and neutrons have no charge and they're therefore neutral. So I'm not really going to talk about mass a lot yet. This will come in later in the session, but there is a way that we can quantify how much mass a individual subatomic particle has on a scale called the atomic mass unit scale. And on this scale, a proton and a neutron have 1 unit, and electrons are so light they're considered to have no mass, essentially. So this is a really handy table to look back at to make sure you've got the basics of atom structure and the way that the subatomic particles contribute to this. Alright, so now we're going to review the definitions of our molecules and compounds just to make sure that we're really clear on this. So remember, the difference is that a molecule can have the same type of atom present multiple times or have different atoms present as well. So a molecule is any group of atoms. In comparison, a compound is a group of atoms that has 2 different elements atoms present. So you can see that for both carbon dioxide and water molecules, they're both considered compounds as well because they have different types of atoms present in those groups. So some definitions that we can go off here. So the molecules being composed of 2 or more atoms, and they're going to be connected via something we call a chemical bond. So a chemical bond is basically a way that atoms connect together. So we'll be looking at exactly how this happens in a later session. So within a molecule, the atoms can either be from one type of element or they can be from 2 different types of element. So in the case of the oxygen molecule, we've only got the single type of elements atom there, whereas in the water molecule, we've got both hydrogen and oxygen elements atoms within that group there. And for the compound, this is where there needs to be more than one type of atom present in the group, and those are going to be again joined by chemical bonds. So you can see for both carbon dioxide and water, they both meet this definition because they have not only oxygen atoms but also carbon for carbon dioxide and the hydrogen in the water, meaning they have more than one type of elements atom within those groups. So what makes water so vital to the human body? Well, for one thing, roughly half the body is actually made up of water. And one thing you might not know is that as well as the body having so much water in it, the cells actually have a lot of water in them as well. So the movement of water in and out of cells actually allows different components to be transferred between cells, which is also really important. So just a couple of reasons why the water content of the body is so vital. So I showed you the periodic table earlier, and the periodic table is made up of different elements. So each element has a different type of atom. And depending on what the atom type is, then it may want to exist just as a single atom, or it might want to try and find a partner to be more stable. So we'll be able to understand more why some of the elements atoms want to come together once we start looking at chemical bonding. For example, something like an oxygen atom wants to grab onto a partner, so there'll be 2 oxygen atoms together, whereas iron atom, Fe, will just be happy enough to remain as a single atom. So as I told you earlier, each element has a different type of atom, and that different type of atom comes down to the number and type of the subatomic particles, and that's the protons, neutrons, and electrons. So for example, for carbon and oxygen, they each have different atoms because they have different arrangements of subatomic particles within those atoms. On the atomic level, all atoms kind of look the same in terms of having that nucleus and the electrons around the outside. The difference between the different types of atoms are the fact that they'll have different numbers of the subatomic particles in the nucleus and around the outside in where the electrons are orbiting around the outside of the nucleus. So that's essentially what makes the atoms different. So there are lots of different types of atoms on the periodic table. In this course, we're only going to be focusing on a select few of them, and you can see the majority of those here. So the ones that we'll be seeing most in this course are carbon, hydrogen, oxygen, and nitrogen. So these are the elements that are present in a lot of the compounds in the body that we'll be interested in, like proteins, lipids, carbohydrates, DNA, and RNA. These are the basis of those compounds that make up life. So they all have quite simple symbols. It's just the first letter of each of these elements is the chemical symbol. So often we'll represent elements by their chemical symbol rather than drawing out the whole name, just for simplicity. So some elements do have two-letter symbols rather than one-letter symbols because there's more than one element starting with C, for example. So for example, calcium is Ca, zinc is Zn. Some of the more complicated names actually have their origin in Latin and Greek. For example, Na, which is sodium, actually comes from the word natrium. And for example, potassium is K because it comes from kalium, Fe, iron, ferrium, etc. So the ones on the right hand side here, you can't really work it out. It's just one of those sort of things you have to know. So we'll only be seeing some of these ones commonly in the course. So sodium is one, Na, iron, Fe, are probably the two main ones that we need to be aware of. So just keep in mind that we've got these chemical symbols as a way of specifying which element we have. So for example, if you're looking at the structure of a compound or molecule, you'll see it written in these chemical symbols rather than the whole name of the atom type written out. Alright, so I'm going to touch now briefly on quantifying matter. So it's all very well to say that we've got a particular type of matter present or it's made up of particular types of atoms, but just like anything, we need to be able to measure it. So measurement is extremely valuable and it allows you to be accurate and also to get things done in a particular way. For example, you can measure the amount of time that it takes you to get to work, so you can try and make sure you're not going to be late. So for a measurement to actually be useful, it needs two separate things. It needs some sort of number value, and then it needs a unit, which will place it somewhere along the scale. For example, if you say it takes you 30 minutes to get to work, the 30 represents the number, and the unit in that case is time in minutes. So we need both of those to make that meaningful. If you just had the number alone, it wouldn't mean anything. If you said it was going to take you 30 to get to work, no one would know what you mean. Do you mean 30 seconds, 30 minutes, 30 hours? They might presume minutes, but they might be wrong. So both having the number and unit together is what we need for a measurement to be useful and valuable. So here are some of the common units that we'll be using in this course. So mass is a big one. Quite often it's in grams or something even smaller rather than kilograms. But anyway, you can measure volume. Temperature is often in degrees Celsius in this course. There's also a measurement of Kelvin, which you might have heard of. Pressure, there's a few different ways you can measure that. One of them is pascals. or atmospheres is another one. Concentration, basically the amount of a dissolved substance in a liquid. So for example, if we dissolve salt into water, we can work out how much salt there is in that water by measuring its concentration. And another important one is a unit of energy, which is something like the kilojoule or calorie. So all of these are units, but they would only be useful if there was some sort of number in front of that unit to be able to quantify how much we were actually counting. For example, if you were trying to measure how much you weighed and you just said, oh, I weigh kilos, that's not really giving any information. Whereas if you said, okay, I weigh 50 kilos, I weigh 70 kilos, then you're placing your number on a scale somewhere and you can work out what that actually means in relation to other weights. So an interesting question to consider now. So I'll give you a few seconds to ponder this one. Why is it that both the number and the unit are important when measuring the amount of water in a dam? Why do we need both? Well, we need both the number and the unit to make sure what we're giving is a meaningful measurement. So we need the number to place our measurement somewhere along the scale. And we need the unit to actually work out what the scale is. So for example, we need both the number, very large number, 2.87 times 10 to the 10 is our number, and then the scale is litres. So if we have both together, then it's an accurate measurement that's meaningful of the amount of water in the Ivanhoe Dam. So what would happen if you didn't have the unit? Well, then you just have 2.87 times 10 to the 10. But the number doesn't mean anything by itself. You don't know what it is in relation to, so essentially it means nothing. Just like without the number, the unit is very much useless, because if you just say there's litres of water in the dam, it's not really giving any specific information. So we need both to create a meaningful measurement. So the next thing I want to have a look at now is scientific notation. So basically this is just a way of showing either really large or really small numbers in a more simple way. So instead of showing it with this decimal point notation where we have the numbers represented like this, in scientific notation we move the decimal point so there's always a whole number to start with. So you can see in the decimal point notation there's actually a 0 here. So you would never see that in scientific notation. It's always going to be a number between 1 and 9. And we do this because it's a simpler way of drawing or writing very small and very large numbers. So instead of drawing or writing 20 zeros, we can actually just do it in this type of representation where we have the scientific notation. So there's a few different parts that we need to be aware of when we're writing the scientific notation. So the first part is what we call the coefficient, and the second part is the exponential term. So it always follows the same pattern of a number, and then we're going to be timesing by 10, and then the power or exponent will be a number between 1 and 10. It'll be a number 1 or greater, and it can also be a positive or negative. So keep that in mind as we go through here. So one way of writing 93 million is what we see here. So this would be considered decimal notation. So it's possible to write this number in what we call scientific notation by moving the decimal point. So the first step towards writing this number in scientific notation is to move the decimal point so that it is placed behind the first whole number. So the first whole number in this expression is the number 9. So essentially we need to move this decimal point from where it is right here all the way up to the gap between the 9 and the 3. And as you're moving that decimal point, you need to count the number of place changes the decimal point has. So for example, you can't just go from this position all the way up to here in one go. So count the number of zeros in between. So essentially, you're going from here to here first. That would be one change. So if we're moving, that would correspond to moving it to there. So that's 1. And then we do that again. 2, 3, 4, 5, 6, 7. So on the 7th one, we've now been able to move the decimal point to where it's required behind the first whole number. So that means we have the number 7, and that number 7 becomes our exponent, the number that we raise to the power of. So we have times 10, and that 7 becomes the number up the top here. So instead of writing it as 93 million, we can now write it as the first two numbers that aren't zeros, 9.3, and then we times 10, and because we had to move the decimal point 7 places, it's now to the power of 7. So if you type that into your calculator, you would actually get 93 million. Okay, so it's just a different way of representing it. And the fact that the exponent, or number 7 here, is actually positive tells you that it's going to be a very large number. So this time we were looking at a very small number in comparison to the very large number we saw last time. So the method for turning it into scientific notation is similar. This time we're going to move the decimal point in front of the first whole number. So what is the first whole number in this expression? We've got all zeros, and then it finally gets to a 3. So the decimal point needs to be in this position here between the 3 and the 7. So the method for moving the decimal point is exactly the same as I showed you on the previous slide, but this time we're moving it to the right. So how many steps do we need to do to get it to that position? So 1 to get it to there, 2, 3, 4, 5, and then 6. Okay, so because we did 6 steps to move the decimal point in front of the 3, the exponent becomes 6. So we write that as 3.7 times 10, and this time it's actually a negative 6. So it becomes negative because we're moving the decimal point to the right. So we can have a shorthand rule for this. So move the decimal point to the right. That means we're going to have a negative exponent. And it also means that the number is going to be very small. Whereas on the previous slide, what we were doing is we were moving the decimal point to the left because we had a very large number, and that means it's actually going to be a positive exponent. So it actually tells you a lot about the number, whether you've got a positive or negative at this final value here, where you're raising to the power of 10. So here it was 10 to the power of 7, positive 7, meaning you've got a very large number. Whereas here, it's 10 to the negative 6, meaning you've got a number much less than 0. Alright, so let's try and put that little mechanism into practice. So we've got a question for you guys to try out now. So the number we've got is 8,310.9. And the challenge here is to express it in scientific notation. So going through that method that I showed you on the previous slides, try and put our number into scientific notation. So now would be a good time to pause the video and have a go at working out which one is the correct option based on the method I've shown you. Okay, so because we have a number that is greater than 1, that means we're going to be moving the decimal point to the left. So let's start by writing out the number, 8,310.9. So we need to get the decimal point between the 8 and the 3 because that's the first whole number. So moving that decimal point, we're going to have to do 1, 2, 3 steps. So that means the exponent becomes 3. So will the exponent be positive or negative? Well, because we're moving it to the left and it's a large number, larger than 1, that means it's going to be positive. So that can rule out B and C because both of these have exponents that aren't 3. Now we're left with 2 options. So if we try and write that out fully now that we've got the exponent of 3, we've got the decimal point between the 8 and the 3, and then we've got the rest of the numbers there. And then that's times 10 to the power of 3. So A is incorrect because the decimal point is actually not between the 8 and 3. And we've also got this extra 0 here, so that makes it wrong. So we can rule out A. So therefore D must be the correct answer. So hopefully you're able to work through that. Alright, so to summarize what we've looked at in this first part of the session, we defined what matter is. Basically, matter makes up everything, and the smallest component of matter is the atom. We also looked at some ways that we can alter matter or change it. So for a chemical reaction corresponding to a chemical change, matter can actually be changed from one substance to another. And the example of this was we saw when methane was reacting with oxygen to produce carbon dioxide and water. The matter that we had at the beginning is different from the matter that we have at the end. And we also looked at physical changes where the matter can change from between different states. So for example, water can change from a solid ice form into a liquid and then into a gaseous form. However, when you're doing a physical change, the identity of the matter doesn't change in terms of its chemical structure. So to change chemical structure, you need to do a chemical reaction. We also had a look at some definitions. The fact that atoms like to come together to form groups, and we defined some of these groups. So a molecule is where you've got atoms coming together to be connected by chemical bonds, and these atoms that come together may be from one element or multiple elements. So for a compound, the group of atoms coming together has to contain more than one different type of atom. So that means you would need, for example, hydrogen and oxygen together rather than just 2 oxygens. And we also saw that the atoms were made up of these different subatomic particles, which are the protons, neutrons, and electrons. We'll go into these in more detail in the next session, in the next part of the session. And we also had a bit of a look at why we need to measure things. So we saw that for a measurement to be valid and useful, it needs both a number and a unit to make it meaningful. And we also looked at how to create these scientific notation numbers, where we've got it in this form of a number times 10 to the power of a positive or negative exponent. So the reason for using this scientific notation may not be that clear yet, but it's basically an easier way of representing really big or really small numbers. And because we're working with atoms and molecules in chemistry, often the numbers we're dealing with are either very large or very small. So it's a lot easier to write in scientific notation than it is to worry about writing too many zeros.